Hello, my name is Josue Castaneda.
And I'm Matthew Bell.
As part of the Cal Poly Pomona SAE Supermileage Club, we built the motor controller for our senior project. In this presentation, we will talk about the vehicle motor controller and end with a quick overview of the vehicle's design and build process. The CPP SAE Supermileage Club is focused on designing and building Cal Poly Pomona's first fuel-efficient electric vehicle. As a new club, we are seeking to create a foundation for future iterations of this vehicle. Our hope is that this current iteration will compete in the Shell Eco Marathon competition. The Shell Eco Marathon competition is held every year in Sonoma, California, and challenges students to develop the most fuel-efficient electric vehicle. The objective of this project is to design the motor controller for the electric motor hub.
A 250-watt BLDC motor was selected to power the 2020 SAE Supermileage vehicle. A BLDC motor differs from a traditional DC motor in that it does not use a mechanical commutator like a DC motor does. A commutator switches the current between phases in order to create the basic rotational motion of the DC motor. A DC motor uses a brush to contact each terminal to receive power from the battery, while a BLDC motor is brushless. Next slide. The BLDC motor used in this design utilizes a three-phase system. Each phase controls when power is delivered to the motor from the battery. The figure shows the three phases of the BLDC motor, along with the corresponding Hall sensor wires for each of the phases. Next slide. Hall effect sensors are often used to measure the magnitude of a magnetic field in order to detect the speed of a rotating object. However, we use the Hall sensors to detect the rotor position. This allows for the commutation of the motor. This is the basic principle of how the power is controlled in this design. The figure shows the three windings of a three-phase BLDC motor. Next slide. When the Hall sensor detects the position of the stator, it signals the motor control circuit to deliver current in the appropriate direction, such that a magnetic field is generated in the exact direction that rotates the stator. The figure exhibits an example of the manipulation of current to direct the magnetic field in the necessary direction. Next slide. The figure to the right depicts the function of the Hall sensors. Based on the figure, when sensor at position 010 senses a magnetic field, Hall sensor at position 011 activates, and current is sent through coil AC to generate a magnetic field at sensor 011. The process then repeats at each position to keep the motor spinning. Next slide.
To begin the design process, we sought out to simply control our motor using an Arduino Uno and stepper motor driver to familiarize ourselves with the code and hardware. We learned from this iteration that a separate circuit was needed to handle the current required to run the motor hub. The Arduino Uno is not able to handle the high amperage requirements of the DC motor and will instead pass through MOSFETs. Our second iteration of the design involved a potentiometer and L298N motor driver. The BLDC motor was controlled by reading the potentiometer analog signals and varying the voltage to the motor accordingly. Our final design of the motor controller combined the two previous iterations with components that could handle the power required to run the motor hub. Each phase of the BLDC motor hub is controlled by a half-bridge driver and two MOSFET transistors, which are rated at 30 amps and 60 volts, which is enough to handle the current from the power supply. The 36-volt power supply required to run the motors is now handled by the MOSFETs, while the Arduino controls when and which MOSFETs are opened or closed. With this final design, we required three different power supplies: a 9-volt power supply to power the Arduino, 12 volts to power the motor controller circuit, and 36 volts to power the motor hub. The Hall sensors of the motor hub were utilized to progress the motor hub from phase to phase. Using donated components and materials on hand, the final circuit was built as shown in these two pictures. Although the motor hub shown is not the motor hub attached to the current iteration of the vehicle, it should operate in the same way. For tuning the e-bike throttle, we found an analog signal range of -90 to 90 was required instead of the traditional 0 to 1023 of potentiometers. Based on the input from the throttle, the motor hub would go forwards or backwards a phase. we were able to remap the range of the signal using the map function of the Arduino code. For future iterations, we are hoping to do further PID calculations to find a more suitable range. There are 3 conditions within the code: stop, forward, and backwards. Depending on the input from the throttle, the motor hub will go forward or backward a phase, or stay in the current phase. With the final design of the circuit built, first stage of testing will be done with the motor hub alone. Using a tachometer, we will determine wheel velocity with any given throttle input. This will give us information on how sensitive the throttle input is and at what increments does the motor hub increase velocity. Once we have access to the physical vehicle, we will attach the motor hub and controller in order to test acceleration of the vehicle. This will be done by timing the speed at which the vehicle is able to travel a certain distance. We wanted to test acceleration when the vehicle was at the final weight, which includes the weight of the shell, chassis, and driver. This will give us a better understanding of the vehicle's performance. As part of the Supermileage Club, we also assisted in manufacturing the shell of the vehicle, designed by Arda Buyukson. The shell mold was CNC'd from high-density foam and post-processed to ensure an ultra-smooth finish. The fiberglass was then laid out and was allowed to set for a few days before being removed from the mold. Some post-processing of the shell was also required. As shown in the pictures, sanding was done to ensure a smooth surface. Once the window space was cut from the shell, the cutout was used to thermoform clear plastic, which formed our window. The entire process took about 6 months to complete.
The vehicle steering wheel began as a simple drawing on a sheet of lined paper. The concept drawing was then modeled using SolidWorks. The wheel was designed such that it would survive the torque and bending stresses it would experience during repeated turns. Filleted edges with large radii and thick cross sections were used to reduce stress concentrations and increase rigidity. It was constructed from ABS plastic, which has more ideal mechanical properties over PLA. Namely, ABS exhibits more strength, ductility, and thermal stability than PLA. Next slide. Once the model was 3D printed, it was covered in wood filler to smooth any imperfections in between the plastic layers. The wood filler was then sanded over the course of a few days until visibly smooth. A 3.5-inch generic TFT LCD module capable of displaying 480 by 320 pixels was inserted into the slot designed for the fitment. It was covered in tape, the gaps were filled, and the wheel was resanded one last time. Next slide. Once smooth, the wheel was spray painted with multiple layers of Plasti-Dip, or durable liquid rubber, and left to dry. The LCD and slot were designed such that an Arduino Uno microcontroller fits directly into the back of the display module. A 1/16-inch steel base plate for the steering wheel mount was then screwed into the frame of the wheel using nuts, split lock washers, plane washers, and adequate machine screw sizing to resist shear forces applied when turning. A 9-volt battery terminal was spliced into the circuit to power the LCD screen. The steering wheel is also able to be powered using the vehicle battery instead of a standalone power source, the 9-volt. Next slide. The figure to the right shows the code proposed to display the Supermileage team logo on startup. Inputting more code in the future would allow for more information to be displayed, such as linear speed and power consumption. Next slide.
That concludes our senior project presentation. Thank you.
Thank you.